All right, new topic. I'm on section 5.4. You'll recall that we talked about the microscopic cross-sectional area, which was the probability of an interaction occurring, and then we took the atomic density. So this was in centimeters squared because we said it represented a target area, and this was atoms per cubic centimeter, and that the product of those two equaled this thing that we called the macroscopic cross-sectional area. Very key. So you can see if I increase the probability or I increase the concentration, the atomic density, I increase the macroscopic cross-section. Well, a new term, and you can remember what this unit was in. When I multiply these terms, this unit was inverse centimeters. This next term is called mean free path. Mean free path. I'm right here in the upper left-hand paragraph under mean free path. It says if a neutron has a certain probability of undergoing a particular interaction in a centimeter of travel, then the inverse of that will describe how far the neutron will travel before undergoing an interaction. So look at here, 1 divided by the macroscopic cross-section would equal centimeters. It would be the inverse of inverse centimeters, which is centimeters. We call this symbol right here, mean free path. So look what's happening. As the atomic density or the probability of an interaction goes up, either one, the macroscopic, the overall probability of an interaction is going up. Therefore, the travel distance, the mean free path, would go down. The neutron wouldn't have to travel as far before an interaction occurred. The next thing on that page is what's occurring with the neutron when it's born. So here's a neutron coming in from left to right, and it has just been born from fission. And remember, let me get right here. It is born in the center of one of these fuel rods in a pellet, and it's going to have to come zinging out here. And it's not going to travel very far. Let me move that a little bit. All right, so the first thing we're going to talk about is what happens to it. Well, here it is, and it's just now, the fission event has just occurred right here. Here's where the fission event occurs. Fission event occurs. Then there's some sort of time before that neutron shows up. Well, you'll remember, for here, less than 10 to the minus 14th seconds was a prompt. But way out here, in terms of this was a timeline down here, this is where it would show up. On average, about 12.7 seconds is when this neutron would show up. Right? So this is called the release time. And there's a big difference in release time. There's a big difference in release time between a prompt neutron at 10 to the minus 14th and 12.7 seconds later where a delayed neutron shows up. This is delayed, this is prompt. We want to talk about now what happens after they're released, all right? And we're going to talk about two things. They start slowing down. When do they start slowing down? When they hit the water. They're going to start those scattering events in the water, all right? So what's going to happen, if we look at it, is here's a pellet, and a neutron was just created here. It's going to travel, and it's not going to see anything that it can scatter very well with because it don't see anything about its same mass. It's just going to bounce off of a bunch of things. Then if there's a helium gap right here, it's going to go flying on through the helium gap, and it's going to get right out here to where we have water flowing. Inside the channel, we have water. And what's going to occur inside that water is the neutron is going to scatter. And each one of these direction changes is where it's hitting a hydrogen atom contained in the water. This is called the slowing down process because each time this neutron is hitting a hydrogen atom, it's giving off energy. And you'll recall We were born way out here in the fast energy spectrum, neutron energy, and the probability of an interaction occurring, an absorption reaction. And that as we slowed down, the probability went up. So we're slowing down in the water doing that, increasing the probability of an interaction occurring because the target area is going up for a lower energy neutron. The process, this first process after it's created, is called the slowing down of the neutron. And then once it's slowed down, it gets to a certain energy level, and we consider it slow, it will continue to slow till it gets to thermal energy. So this length here is the straight line distance, is called the slowing down length. Then it continues to slow down. At this point in time, once it's slowed down, it's thermal. It's at equilibrium with its surroundings, and it's going to bang around until it finds something to absorb into. We call this distance here the thermal diffusion length. We call this the slowing down length. The slowing down length is actually the straight line distance. Straight line distance. And the thermal diffusion length here is the straight line distance. Slowing down length, straight line distance between the point of birth to the point that we consider it slowed down. The time associated with that would be called the slowing down time. Once it's thermal, till it gets here, once it's thermalized, it gets absorbed right here. Absorbed. That straight line distance is called the thermal diffusion length, and we call that the thermal diffusion time as the straight line distance. Now, I use L sub TH to, just so you'll know, so the total distance would be this. Your book will sometimes just use an L. I like to put the TH as a sub symbol there so you understand we're talking about the thermal diffusion length. Excuse me. So we're going to be looking at this a lot. We're going to go over it again and again and again. On the left-hand side, slowing down length. The neutron begins to slow down. Phase 1 slows down. It says the straight line distance between the point of birth and thermalization is called slowing down length, and the associated time is called the slowing down time. It'll continue to slow down until it gets absorbed. So the straight line distance between the point at which it became thermalized and the point where it gets absorbed is called the thermal diffusion length, and you'll see that's an L right there where I use L sub TH, and the associated time is called the thermal diffusion time. There's an important note right here, right? M is called migration length. M. It's equal to slowing down length plus thermal diffusion length. So that's just, here's the neutron born in the pellet. There it is. Neutron born. It's going to leave the pellet, come to the water. Here's the neutron. Now it is thermalized. So from here to here is the slowing down length. The neutron is fully thermalized now. It's at equilibrium with its surroundings. It's a thermal neutron. Right here, it gets absorbed. Absorption. We call this thermal diffusion length. There's a certain amount of time here and time here. We'll call this the slowing down time, thermal diffusion time. The sum of slowing down and thermal diffusion is the overall length, straight line distance, which is the migration length. Now, what would affect these lengths? That's key. You have to ask yourself, what would affect how far this neutron has to travel? Well, what is it colliding with to slow down is the question. And the answer is water. Keep that in mind, right? It's colliding with water. So, some review up here in the upper right. Some review, it says, okay, don't forget, prompt neutrons are produced at an average energy level, 2 mega electron volts, and they immediately begin to slow down by scattering with target nuclei. That target nuclei is water. Delayed neutrons, they're born at a lower energy level, and they too begin to slow down by scattering with water. After a bunch of collisions, it says, the kinetic energy of the neutron will be reduced such that it has about the same average energy as the surrounding atoms. We're going to call that thermal. And the definition of a thermal neutron for us when we're at about our operating temperature is it'll have about 0.049 electron volts. So I'm at thermal equilibrium. Remember, 1 electron volt was slow. So this thermal neutron is also a slow neutron. A note there says, don't forget the thermal neutron is one that's at equilibrium with its surroundings, and it could occur at any energy level. The process that we're talking about of this prompt and this delayed neutron banging around in the water and slowing down so that it can increase its target area and become reabsorbed, this is called thermalization, slowing down, or moderation. And we're going to be using these terms a lot. As we attempt to thermalize a neutron, we're trying to encourage it to slow down. In the moderator is the medium in which the neutron is slowing down. And in our case, our moderator is water. All right, the material used for the purpose of thermalizing neutrons is called a moderator. Define thermal neutrons. Knowledge requirement. Thermal neutron is one that is at thermal equilibrium with its surroundings, and it can occur at any energy level. For us, though, thermal neutrons occurred at around 0.049 electron volts. We turn the page. We're going to have some practice questions here in a minute.